Welcome to Otterbein University, Westerville, Ohio, where Professor Daniel Mendelsohn in his thermal science lab is going to talk us through 2 experiments using TecQuipment's Vortex Apparatus, the H13.
All right, this is the H13 Vortex Apparatus, and we're going to have Liam and Rachel demonstrate the measurements that we take. Here, we're starting out with the forced vortex experiment where we have this fixed volume of fluid in there about halfway up. And as we spin the fluid, we create a vortex. So let's crank her up. And, power on. It's essential. And kind of takes the fluid a little while to catch up. Okay? You can slow the motor down, but it will still be rising. Faster. So you can see the piece of tape there that's rotating around. That tape is for measuring the angular velocity. When we get to a stable vortex at a fixed speed, okay, we'll measure that by counting the number of revolutions and using a stopwatch to see how long it takes for 10 to 15 revolutions. All right, we're getting there. We're starting to see a ball. Alright, a little faster. Let's see what that does. So it's all wobbly, right? That's not steady state and that's not a vortex. We want a real clean, stable surface. So leave the speed and let it stable out. Get it. Alright, that looks good. All right, so now with the stopwatch, okay, so your phone, okay, we're going to measure the angular velocity, so do a count when you see the tape at the same place each time. Yeah, see what I mean? It keeps going, it keeps rising. It takes a while to steady state. I think we're safe there. It's a little slower, we don't want to touch the supply pipe. Alright, so let's measure the angular velocity. So we start the stopwatch and count, let's say 15 revolutions.
Alright, that's about 9.51 seconds.
Okay, for how many revolutions?
10.
Okay, so we turn a revolution into 2 pi radians, and we get radians per second. Okay, let's do the measurements. Okay, so do a sample measurement of the profile with the ruled pointer. The bracket fixed, so into the bracket there. So you see it piercing, just piercing the surface. You read off that distance and you record that, and you do that at about 10 different values of radius. You slide that bracket left and right. So do one on the other side. We do it on both sides. So we get 2 sets of data. And they should be the same, left and right, but they're usually not exact and we average them. All right, and now let's do a sample measurement of the head, okay? We use the Pitot tube, and that open end of that tube should point into the flow, as straight into the flow as you can get it. Okay, and you'll see that it pushes water up into the tube. And you read off that height, okay? While it's down, all right? One on the other side. Change the direction of where you're pointing that to into the flow. All right, and that measures what's called the head, which is a measure of total energy of the flow. All right, so that's the force vortex. Let's shut her down. all the way. empty the tank. And this is a prelude to the next one. We're going to drain, but we're going to do it in a different way. So when that's drained, we'll put in the inner cylinder. So we take the crosshatch off, the crossbar off. It's got a little groove it sits into. All right, we're actually just about ready. So now you turn on the pump, the supply, and we want to reach a steady state. So first let's add more water. Let's beat more water in and out for a little bit. But then we want to balance it, the same amount in as out. All right, that's a pretty good whirlpool. So that's a free vortex. We haven't spun one yet. All right. That looks good. Let's spin it. You do the same thing here. Once you set up the vortex, you measure the angular velocity. But you see the different shape, completely different shape. So reminiscent of your bathtub drain, sink drain, tornado. Alright, that's a pretty nice steady state structure. So now we do the same thing, we measure the profile. That's it, actually, we don't measure the head, just the profile. So let's do a sample of that. Okay, so now when you change the conditions, see what happens? You get that really cool structure, which is not an axisymmetric vortex. And that's what we're trying to get. Fun to look at.
Just wait for it to
Yeah, wait for steady state, and then we'll take a measurement. So in the forced vortex, the whole chunk of fluid rotates as a rigid body. Here, at each different radius, there's a different velocity. The angular velocity gets bigger and bigger as you go to the center. All right, that's pretty good. So let's take a sample profile measurement. All right, so when you record all this, we'll plot it up and compare it to the theory and talk about why it doesn't match up.
What's great about the H13 Vortex apparatus is how it allows us to tie the fluid mechanics into the laboratory and vice versa. It also gives us an opportunity to talk about experimental error. So let's take a quick look at vortex flow. So vortex flow means that all the fluid particles are rotating about an axis, the z-axis here, and they all fluid particles have an angular velocity about that axis, think degrees per second, and a tangential velocity, which is equal to the angular velocity times the radius, which is how far the particle is from the axis of rotation. Two of the major principles of fluid mechanics, Bernoulli's principle, which is an energy balance, and Newton's laws, think F equals ma applied to rotation. Those two principles allow us to theoretically predict what the velocity profile is, what u of r is, how the velocity depends on the radius, and as well as the shape of the vortex, the profile, z of r, which is characterized by the pressure being equal to atmospheric pressure. We can also predict what the total head is just under the surface, and that's a measure of the energy of the flow, which has contributions from the pressure, from gravitational potential energy, and from kinetic energy. With that theory, we predict two possibilities for a vortex. The left is a forced vortex where there's a torque turning the fluid around, and in that case, the angular velocity turns out to be constant everywhere in the fluid, so that means that fluid's rotating like a rigid body, like a chunk of jello, think, all with the same omega everywhere. And in that case, we predict a surface profile that's a concave up parabola, that's the solid z curve, and the head is also parabolic, equal to twice the value of the z. And on the bottom, we see that the velocity increases from 0 at the center to a maximum out at the outside of the whirlpool, of the vortex. The free vortex on the right, that's the opposite. The speeds get bigger as you go in, and the free vortex is typically formed by allowing the fluid to drain out through the bottom here and rotate the fluid at the same time, and what we end up with is a whirlpool. Think of the water flowing down your drain. In that case, it's the head that's constant everywhere, and the angular velocity changes. It's biggest in the center, and as you move away out in larger radius, it gets smaller. So, and the shape of the profile is 1 over r squared, okay, not a parabola, the inverse of a parabola, and so it looks like this figure. So let's see what the experimental results show. So the orange on the left for the forced vortex, the orange squares are a measurement of the surface profile with a very accurate stylus that we can get a pretty accurate reading for that surface profile, and that those orange squares do fit to a parabola quite well that matches the theory quite well. However, the head, you can see that's not the case. The head's supposed to be twice, theoretically, it's supposed to be twice what the z value is, okay, and clearly it's not, and it gets worse as you move out in higher radii. Most of that is most likely due to the way we measure the head, which is with a handheld Pitot tube, and that has inaccuracies in how you hold it, the direction, the orientation, has inaccuracies in how you read it, and that is most likely where the error comes from here. The free vortex results on the right, the symbols are measure the profile. That though data does fit quite well to 1 over r squared and would allow us to calculate the unknown constant that's in the theoretical solution on the previous slide. So that's the experimental results in the theory in a nutshell, a great way to visualize and see what's going on.